In the name of God, hi everyone, I'm Mahmoudi. I'm so honored to be presenter of improving LoRaWAN scalability for IoT applications using context information article. Let us start by taking a look at what we want to talk about in this presentation. As you can see in the left side, we will have an introduction. Then I'll giving you some background information about the topic. In the related work section, we introduced what we have done in this research in the proposed method part. Then we evaluate our proposed method with a scenario that I will talk about in the evaluation section. And finally, in conclusion part, we state the conclusion and obtained result. Let us start introduction with talking about general concepts that we need to have before going to the subject. At first, as depicted in the graph, we can see that different technology work in different ranges and with different data rates, so we can compare them. As you can see, Bluetooth, BLE, 6LoWPAN and Zigbee work in short range and with low data rate. Wi-Fi technology is also in short range but with more data rate. As far as range of coverage goes, we have cellular technologies such as 2, 3, 4 and 5G, which cover more than the range of short range. And after cellular, we have long range technologies such as VSAT and LPWAN, which cover more than cellular technology but with lower data rate. So LPWANs are suitable for applications that there is not a lot of data and we want to send data in long range, such as alarming systems, that there is no need to transmit a lot of data, and for example 1 bit is sufficient. If we have a lot of data, we have to use other technologies like cellular. There are some circumstances that using LPWANs is not so optional, and we have to use them, especially when energy consumption of devices are important or when accessing the devices are difficult. For example, when the device is installed in woods where have wild animals and everything, it's better to use LPWANs. When we need to update the device firmwares or we need not to replace the battery of devices for a long time. LoRa is one of the LPWAN technology. In fact, most important ones are Sigfox and NB-IoT and LoRa, but LoRa is more popular because of industry support like LoRa Alliance, IBM and Cisco. We will talk about LoRaWAN protocol stack a few moments later. About end device classes in LoRaWAN, as you may know, there are 3 classes, A, B and C. LoRaWAN network in its base form has negative point. One of the negative points is that there is no mechanism, especially when using class A and devices in the network, for guarantee the network reliability and scalability, because in this class the mechanism to control access is such as Aloha protocol. This figure shows the LoRaWAN protocol stack. You can see the classes in the LoRa MAC layer. This figure shows the LoRaWAN protocol stack. You can see the classes in the LoRa MAC layer. As you may know, the word LoRa refers to 2 different concepts. The first is LoRa protocol, which is a physical layer protocol that uses unlicensed ISM frequencies and uses CSS. And second is LoRaWAN protocol stack, including 3 layers: physical layer, media access and application, that uses the LoRa physical layer protocol. In this slide, you can see a typical LoRaWAN network architecture. There are some end nodes in the left side which have connection with gateways by LoRa RF and LoRa MAC communication type. Gateways communicate with network server by 3G Ethernet backhaul, which is a TCP/IP SSL connection and uses LoRa MAC. And finally, network server or network servers communicate with application servers by TCP/IP SSL connections and secure payload. After LoRaWAN description, let's talk about IoT. IoT consists of objects connected to the internet and can be controlled and managed. IoT is different from sensor network. One of the differences is that in IoT, objects are connected to the internet. Another thing that we explained before talking about proposed method is context awareness. Purpose of context is any information that pertains to a particular entity or object. To better understanding, let's review its life cycle. Context information life cycle: information gathering, modeling, reasoning, and distribution. In the reasoning level, there are some techniques like supervised and unsupervised learning, rules, fuzzy logic, ontological, and probabilistic reasoning that can be used depending on the application. Each technique can be used in a specific application. For example, for situations where the feature set is easily identifiable and outcomes are clear and large datasets are available, like activity detection or missing value detection, it is better to use supervised learning like artificial neural network, Bayesian network, case-based reasoning, decision-tree learning, support vector machines, and everything. But for situations where the output is unknown, for example, like detecting unusual behavior, it's better to use unsupervised learning like clustering or k-nearest neighbor. After selecting the reasoning method and implementing it, the next level is distribution. There are two methods for that, query and subscription, that also called publish subscribe. After introduction of the main concepts and generalities that have been stated, we will review the history of previous research on the subject. For better use of time, I have summarized the research in a table that you can see it in this slide. In the for reference, which was presented in 2019, high-density urban environment in two modes, confirmed and unconfirmed, has been studied, and at the end of the day, the conclusion that reached is increasing the height of the antenna can significantly improve performance in an urban area. In the reference 5, which was presented in 2018, for reduce packet collisions in the network and thus improve reliability and scalability, researchers provide a protocol called LoRaWAN. In this protocol, what needs to be done at the gateway is that dynamically determine the received signal strength and SF for each channel, and what needs to be done in nodes is determining the transmission power, SF, and channel and time for transmission based on the information provided by the gateway. In 6, researchers provide SF control algorithm to reduce PER or packet error rate to improve fairness and throughput. In 7, an SF allocation plan provided for massive LoRaWAN network to avoid congestion and package collisions. Reference 8, by experimental measurements of coverage range and packet loss rate, provided an automatic mechanism for selecting the LoRa transfer parameter. A review of previous studies, some of which you can see the most important of each category in the table, shows that the focus of the articles was more on improving performance by intelligibly adjusting system parameters. The proposed solutions are mainly based on the internal status of the network to adjust the parameters. Also, the review of contextual awareness articles in the LoRaWAN network has been mainly focused on the specific application that the network has been implemented to achieve that application, and has not dealt with the LoRaWAN network itself. Using contextual information to improve the performance and efficiency of the LoRaWAN network is a topic that has received less attention in articles. Given the number and variety of applications of LoRaWAN network used in the Internet of Things, context-based customizations that led to better performance of the LoRaWAN network will become increasingly important. Therefore, the present study can be a model to benefit from context information to improve the performance of the LoRaWAN network. As we mentioned in the previous slide, the proposed method use contextual information in addition to the internal information of the network to schedule the nodes in the network. Figure depicts the proposed design architecture. The figure shows a typical LoRaWAN network with sections added to the network server. As you can see, two sets of information are used to schedule nodes. Information taken from the context that is prepared by going through two steps: context gathering and context analysis, which we will explain in the next slide, and information that comes directly from the internal network. At first, we have gathering context information from resources like meteorological information, road traffic, user mobility, ambient noise and lighting, and other resources that may use. In context analysis step, we identify, sort, organize, interpret, integrate, and communicate contextual data The output of this step is the information that we need to use in the scheduling step. And in the time scheduling step, we use informations that obtained from previous level and directly obtained from internal LoRaWAN network. In order to evaluate the proposed solution, a forest fire alarm is assumed. The forest fire alarm system operates in such a way that it sends an alarm if there is fire condition in the forest. It is assumed that smoke sensors are installed in different parts of the forest and are set up that as soon as they wake up, they perform the measurement and send the information. The network server is supposed to send the next wake-up time with a sensor after receiving information from the sensor. Upon receiving this message from the server, the sensor set its next wake-up time and sleep. The server is supposed to calculate the time of the next wake-up of the sensor according to the situation inside the network, density, service quality need, and so on, as well as the context information that receives from outside of the network like meteorological organization. An example of past meteorological information is shown in this figure. The last column of dataset is criticality, is the tag of the row. This slide shows some of the codes and pseudocodes that used in the evaluation of the proposed method. In the first row, the new predict is obtained from the context 2, 3, 4, 5, and 6 rows. Make the parameters that we need to pass to the insert and return time function. And the last row sets the node period by the calculated time. The second figure depicts how we build and use decision tree in Python to predict the degree of criticality based on context information. But setting the next wake-up time of each node is not enough, because we need to make sure that this time is not recorded for more than a certain number of nodes, because the same waking times of a large number of nodes will lead to more collisions in the network. The operations of the modeling process of storing the wake time of a node in database are performed in the insert and return time function. The simulations were performed with and without our research scheduling time calculations, and you can see the result in these diagrams. The left one is the comparison of collisions, and the right one is the comparison of the energy consumption of proposed method, which is the blue line in the chart, and baseline, which is the default LoRaWAN network in the simulator, and is the orange line in the chart. As you can see in the next slide, for conclusion, using our proposed method reduced congestions by 51% and energy consumption by 52% in average. The simulations are repeated for many times, and in all of them, in terms of the number of collisions and in terms of the energy consumption, our proposed method is better than the base LoRaWAN network. At the end, I have two suggestions for anyone who is eager to continue this research. As future work, working with more than one gateway will develop the solution, and combining the proposed method with SF tuning techniques could open the new way for new research. And thank you for your attention.